You know, every single time you stream a movie or you hop on a video call, you're actually tapping into a massive global network made of pure light. Well, today, we're going to pull back the curtain on the incredible unseen craft that makes our entire digital world possible, fiber optics. Let's dive right in.
Just look at this. I mean, it might seem like some kind of abstract art, but what you're seeing are the real veins and arteries of our digital world. These are actual, physical strands of glass, each one thinner than a human hair, and they stretch for millions of kilometers across continents and deep under oceans. It's not magic, it's infrastructure. And wow, it is beautiful.
So, it's one thing to imagine this giant global network, right? But it's something else entirely to actually build it. And the real challenge, it all boils down to this one simple question. How on earth do you perfectly join two microscopic strands of glass so that light can pass between them with practically zero interruption? This is where high-tech engineering meets this painstaking, hands-on craft.
And that brings us to the real heroes of this whole story, the technicians. You gotta forget everything you know about just plugging in a cable. Connecting fiber optic lines is basically a form of modern art that demands just incredible precision and skill. You see, before a single photon of data can be sent, the fiber itself has to be prepped. And this isn't just, snipping a wire. Any tiny mistake here, even one that's totally invisible to your eye, can completely ruin the connection. It all, and I mean all, begins with a flawless preparation of the fiber's end.
Okay, let's just walk through what a technician has to do for one connection. First, they have to cut through the rugged outer cable. Then they meticulously, layer by layer, strip away these protective coatings to reveal the bare fiber. After that, the exposed glass has to be perfectly cleaned of any residue. And then, finally, comes the most critical step of all, cleaving the fiber. This isn't a cut, it's a highly controlled, perfect break.
And to pull this off, technicians use a really specialized toolkit. We're talking about things like hot knives just to get through the sheathing, high-precision cleavers to get that perfect break, and even polishing films to create a surface that's as smooth as a mirror. These are not your average tools from the hardware store. They're designed for microscopic accuracy. This is some serious precision work.
Okay, so the fiber is stripped, it's cleaned, and it's been perfectly cleaved. Now what? Well, now it's time to actually make the connection. And there are basically two main ways to join these incredibly delicate strands.
So you've got two main methods. On one hand, you have what's called a mechanical splice. Think of it like a tiny, ultra-precise little house that just holds the two fiber ends in perfect alignment. But on the other hand, you have the gold standard, fusion splicing. This is where a machine uses an electric arc to literally melt the two glass ends together, welding them into a single, continuous strand. This creates the strongest, most seamless connection you can get, with the absolute least amount of signal loss.
Let's just zoom in on that cleaving process for a second, because it's so important. It's really the same idea as cutting window glass. You score it, and then you apply tension to make a clean break. But for fiber, this has to result in a face that is perfectly flat and totally perpendicular to the fiber's axis. Because if it's even slightly angled or jagged, light will just scatter everywhere and the signal degrades. Think about it. The light expects a perfectly flat doorway to enter the next fiber. An angle is like a ramp, sending those photons bouncing off in all the wrong directions, and poof, there goes your precious data. So a perfect cleave? Yeah, it's absolutely non-negotiable.
And this right here, this is the end result. All of that incredibly meticulous work ends up housed inside connectors just like these, modern LC connectors. They're super small and efficient, which allows for just massive amounts of data to be transmitted through data centers. Every single one of those little white plugs holds the result of a technician's careful, steady hand.
But look, making a perfect physical connection, that's only half the battle. Now we have to switch gears, from the technician's craft to the engineer's science. We have to make absolutely sure the light itself is strong enough to actually complete its journey.
This is the key question for any network designer. You've made a perfect splice, that's great, but can the light signal survive a trip over 10, 20, maybe even 100 kilometers? The answer lies in calculating something called the optical power budget.
To put it simply, the power budget is just the total amount of light loss a signal can handle before it becomes too weak for the receiver on the other end to even understand it. It's the engineer's playbook for making sure the signal is going to arrive safe and sound.
Here's a really great way to think about it. Imagine the light is water, and the fiber optic cable is a really, really long garden hose. You need enough water pressure or light power right at the start to make sure that even after traveling the full length of that hose and losing some pressure through tiny leaks, which are like our splices and connectors, there's still a strong enough stream coming out the other end. So how do we actually calculate this? Well, first things first, we need to know how much power we even have to work with. We take the power of the transmitter, that's the device sending the light, and we subtract the sensitivity of the receiver, which is just the minimum power it needs to see the signal. That gives us our total available power.
All right, let's use a real-world example so this makes sense. Power in fiber optics is measured in something called dBm. Don't worry about it too much, it's just a way to talk about signal strength. So imagine a transmitter that puts out -10 dBm of power. And way over at the other end, the receiver needs a signal of at least -33 dBm to work right.
The math itself is pretty simple, but you got to be careful with those negative numbers. We subtract the receiver's sensitivity from the transmitter's power. So that's -10 minus -33.
And that gives us a total available power budget of 23 decibels. This is our light budget. We have 23 dB that we can afford to spend on signal loss along the way before that signal just becomes too weak to read.
Okay, now for the fun part. We have to identify every single thing along that fiber's path that is going to spend from our 23 dB budget. We basically have to account for every single leak in the hose.
And what are those losses? Well, the biggest one is usually what's called cable attenuation. That's just the natural dimming of the light as it travels over a long distance. Then you have loss at every single connector you plug in. You lose a little bit of light at every single splice. And of course, smart engineers always add a safety margin, to account for future repairs, aging equipment, or even changes in temperature.
Okay, now let's see it all come together. If you look at this table, you can see we start with our 23 dB of available power. We subtract 10 dB for the 20 kilometers of cable, we subtract another 4.5 dB for the 6 connectors in the line, and we subtract a tiny 0.4 dB for 4 different splices. That leaves us with a link margin of 8.1 dB. Finally, we take out a 3 dB safety margin, just to be safe, and we're still left with 4.6 dB of excess power. Since that final number is positive, we know for sure this link is gonna work.
So, we've gone from the microscopic world of a single strand of glass all the way to the complex math needed to span an entire city. So now, let's zoom all the way back out again.
This is the incredible intersection of it all. You have the hands-on, precise craft of the technician getting a fiber ready, and that very act makes our entire world of high-speed microelectronics and global communication possible. Every silicon chip, every data center, all of it relies on millions upon millions of these perfect, almost invisible connections. So, the next time you connect to the internet, just take a second to remember the hidden craft that lies beneath it all. A global network that was literally built one perfect splice at a time. It really makes you wonder, with each new connection being made right this second, what future possibilities are we lighting up right now? Thanks for joining me for this explainer.